you should be able to see my screen now. If not,
Yep.
just let me know.
Yes. Yes.
Perfect. So the topic today is graph databases, and especially graph databases for machine learning, or how you can use a graph database to help you in your machine learning task. So a few words about myself, but it has actually already been said, most of it. So I started with a PhD in particle physics, and then I moved to the data science field. I've touched different domains such as relay state or mobility, and now I'm working on some logistics related tasks. And I'm using graph databases in different aspects of this work to talk about, to model a road network, for instance, for travel time estimation and stuff like this. So you can find me on Twitter, on LinkedIn, and on those social media. So the talk today is about graphs. So I will first try to explain why graphs are important and can help us in making better prediction in machine learning. Then I will introduce graph databases with a special focus on Neo4j. I will explain you why. And I will also talk about a graph algorithm and the graph data science library included into Neo4j. And finally, we will go toward graph deep learning. I will say a few words about graph embeddings and graph neural networks. So graphs. As data scientists, I would say we are used to see observations. So basically rows in a CSV file or in any data store. But we are not used to see the connection between them. So we are just seeing points, but we do not see how those points are connected. And seeing some connections, you can identify patterns in your data that you are not able to see otherwise. For instance, here you see that we have connected the dots, the red dots, and you see one pattern, and you can maybe extract some information that, for instance, you have two types of, if the dots are users, you can see two types of user or two groups of users, the red and the right and the left one. And with the same observations, if your relationships turns to be totally different, your conclusion about your data is also totally different. If with the same dot we have this kind of relationship here, we do not have two groups of user, we have one group, and the user with ID 4 is the kind of the central user whose all the other users are connected to. So the pattern is totally different, and the conclusion we can draw from our data are also totally different. So some examples of network you might already have in mind. Of course, you can think about the social network like Facebook, Twitter, or whatever other social network we are used to see now. We also have road networks and any other type of network, such as computer network, or the internet itself is also a graph. But there are many other examples of graphs that have been built in order to really model the relationships between the entities. Here are a few examples where, for instance, researchers have built a graph of protein interactions in order to infer protein characteristics and where they could be useful. There are also a graph about stock market and financial transactions in general to identify fraud. And there is this new, I would say, sorry. There is this knowledge graph, so this concept of knowledge graph that also rises a few years ago. So it's a bit hard to define a knowledge graph. If you if you Google it, you will have some problems to find a real definition. The closer I could find to what I think knowledge graph really is this. So it's a collection of entities. So either can be users, it can be products, it can be movies, actors, it can be whatever entities, and also some abstract concept like is it a fraud or not or whatever, and you basically try to connect all those entities. So let me give you an example which is related to the current context. Some users have been building this COVID graph using Neo4j, and their goal was to connect a lot of research, or basically all the research that was done about the COVID pandemic, and all the papers that were published to study different medicine, different vaccine, and all this kind of stuff. So they have connected all the papers, all the different possible medicine, the side effects, and everything into one single database, and to help researchers finding connections that will be very impossible to see among all the thousands of papers that were published about these topics during the last few months. So if we stay like this, I mean, we are just putting our data in a graph, and I would say it's just yet another data store like SQL or MongoDB or anything else. And the question for us is how can this knowledge about the connections between our observation help us make better predictions? And as a few examples, before going into the graph database world, you can think of if you're able to measure node similarity, or how two products how two products are similar, or how the user, or how the behavior of your user are similar, you can use this information to make a recommendation, for instance. You can also use this graph pattern to identify fake news or hoax. For instance, it has been used to identify fake information on Wikipedia by identifying the articles that were not connected to articles that were known to be true. And you can also use it to identify communities into your graph, whatever your graph is representing. So this is really abstract. We're talking about graph, we're talking about network, about knowledge graph. But the question is how we do that in practice. So one solution, of course, is to use graph databases. So graph databases, the interest has been increasingly growing during the last years, as you can see on this chart showing the trend interest. And the green curve at the top is the one concerning graphs databases. So it's used as a replacement for SQL or for any data store. And we will see that we can use it as well for machine learning. So trying to draw a full landscape and an exhaustive landscape about graph databases is merely impossible. But here I just wanted to show you that there are many actors on the market. Amazon has its own flavor of graph databases, Redis, and that's only the one I've heard of. So there are many, many others. So they differ in many ways. They differ in their nature. For instance, well, Redis graph is based on a key value store that's turned into a graph. MongoDB is also different because it's a multi-modal database. So they are basically building a graph from a document database like MongoDB is. One also very important difference is that they differ in the query language they are using. So there is not yet a unified graph query language, and each vendor tend to have its own query language. So it's not totally true. There are a few a few languages that are used by several vendors. One of them is Cypher, that is used by Neo4j and Redis Graph, and it has some really good advantages, especially that you can, it's really visual and you can learn it very quickly. I will show you some examples in the following. So among all these databases, I've chosen to use Neo4j, and I will show you examples using Neo4j in this talk. The reasons, there are many of them. First, they do have a lot of free content online, from blog posts to video to books. And it's really easy to get started with Graph thanks to this content. They also have a very big community that you can so that you can easily find help if you have any problem with setting up Neo4j, importing your data or whatever. So it's very useful. And finally, they are organizing several events all year long, from meetups to Twitch sessions. They also organizing conferences to really showcase what you can do with a graph database, and especially with Neo4j. So that's all that is not directly related to Neo4j. So they have a lot of content, that's good. But now what can you do with Neo4j? So Neo4j is what is called the property graph model. That means you have a graph, and each of the entities in the graph can have some properties. We will see that directly after that. They do have drivers in many languages, including Python, so you can grab retrieve information from the Neo4j database with Python, and especially with Jupyter Notebook. And two main important points to me is that their query language is Cypher. So as I already told you, it's very, very easy to learn and very visual. So it's really good. And last but not least, they have an officially supported graph data science library, where they implement many graph algorithms that we can use to better understand our data and to build features. So the property graph model. So here is an example of data that can be stored into Neo4j. And you can see that it represents two persons, one with name John and the other one named Sally, where we can see that those two people are friends. And both of them have read a book called Graph Databases. So the point here is that this is what is stored into your database. There is no need to think about adding a foreign key somewhere or anything. Both the entities, the persons and the book, and the relationship are stored in your database as they are displayed here. So if we break down a little bit the different pieces of information in this on this drawing, you can see that we have actually three nodes, so two person and one book, and the nodes have a label that helps differentiating the type of node we're talking about. So we have two person and one book. We also have relationships, and relationship can have a type. So here a friendship or a has read relationship. And it's important to note that here we have only, for instance, between the person John and the book, we have only one type of relationship, which is has read, but we could also have different type of relationship, for instance, has written or anything else. Regarding the relationship between the person and the book. And finally, on top of the nodes and the relationship, we can attach properties to each of these entities. So a person can have a name, an age. A relationship can also have a creation date. And for instance, here we have added on the person and on the relationship between the person and the book, the rate that person gave to that book. So as you can see, Neo4j is actually schemaless. So that means that you can add a property on a node and not on another. That's the case, for instance, here where we have the age for John, but not for Sally, for instance. So let me give you a few examples about how Cypher works. So here is the first query we can write where we are actually selecting all nodes with the label person, which basically is just used by using this colon here and then writing the name of the node. If we want a single person, for instance, so if we want to retrieve only John, then we can use a where clause where we will filter on the name and the property attached to this node. The last cipher where we have the use of these curly brackets is just a shortcut compared to the previous one with the where clause. So the last two queries on this slide are doing exactly the same thing. So we can match one person and select one person, but the power and the real advantage of graph databases lies in the fact that we can traverse a graph by following a relationship. For instance, we can find all the books read by John by using this query. So we start from the node John, then we follow the relationship has read up to a book, and we just actually select the book matched by this pattern. One application of this is that we can easily build some recommendation engine by using simple Cypher patterns. For instance, we can look for books read by my friends. So I start from a person, let's call John. Then we look for his friends by following the friendship relationship. And then from the friend, we follow another relationship, which is the has read up to a book. And we only select those books. If we want to be a bit more precise and exclude the book that John has already read, we can start with the exact same query and add a where clause to exclude the book that John has already read. So that's very easy, I think, to understand, and to really, you can easily write some recommendation like this without very complex models. We can add more complexity to the query, of course, if we want, for instance, to select only the books that have good enough rates, meaning that my friends have read it and they also have liked it. And here we do basically, whoops, sorry. Here we do an average on the rates given by our friend. So that's one example of about a recommendation. I went a bit fast. There are other applications of graph databases using the exact same principle. I mean, just using the fact that you can traverse the graph very easily. You can use it, for instance, for fraud detection. And another example would be to use it for fake news detections. So here is another pattern where you see that you have 3 users that have been found to use the same IP address, and the 3 of them have shared the same post. So it's probably a suspicious behavior, and it would be worth checking a bit further whether these users are real users or correspond to fraud behavior. So this was the first part where I wanted to show you how by just analyzing and traversing your data, you can already, without any complex analysis, extract some information from your graph. Now I will show you a different algorithm that you can run on your graph. First, to understand your data. So we will be able to extract some clusters in our data, for instance. And the other use case for a graph algorithm is to create new features. So if you're trying to do node classification, for instance, and you are able to add as a feature that some nodes belong to the same community, you can enhance your predictive power. So there are different types of algorithm when we talk about graph algorithm. One of them is the shortest path algorithm, which is maybe the first one that come to mind when we think about graph. But hopefully that's not the only one. That there are what we call a centrality algorithm. So centrality is used to measure node importance. Node importance is, for instance, how popular a person he is on Twitter, for instance. That's one way to measure importance. Then we have community detection, which corresponds to node.
Sorry, you're on mute. Can you unmute? Sorry.
Hello?
Yeah, thanks.
Okay. No problem. So I don't know where you lost me.
After community detection.
Okay, so it was just we missed nothing. So so after community detection, another type of algorithm that you can find is a way to measure node similarity. So node similarity is based on the node context. So if two nodes are connected to the same node, they have some similarity, while if they are very far apart in your graph, the similarity is less important, for instance. So do you have different types of metrics to measure node similarity depending, again, on your data and what are the patterns in your data, what are the processes creating your data. In the same way, there are link prediction metrics, which is another important use case for a graph algorithm. And the goal is to, given two nodes that are not connected now, whether there is likely to be a new connection appearing between those two nodes in the future. And last but not least, we have this node embeddings algorithm, where you basically transform your graph into a matrix by preserving your graph structure. I'll give you some details about that very soon. So graph algorithm, you can find some implementations, different packages. One of the big advantages of Neo4j is this Neo4j Graph Data Science Library, the GDS, where there are more than 50 algorithms implemented for each of these types of algorithm. And it's really super easy to use. So just here is basically some visualization about centrality algorithm, so the way to measure importance. One of the algorithms is called PageRank. It has been used, and it's still used by Google, to rank their results on their search engine results. So it's a really important algorithm when we talk about graph. And here is an example of community detection algorithm. So on this picture, we have identified 5 communities with a given algorithm. So I just want to show you now how we do this, how we can basically run an algorithm with Neo4j, and how we can extract the data from this algorithm to use into a machine learning model. So here I have created a graph which contains a few nodes, so almost 1,000 nodes. So it's quite a small graph. It's just there for the demonstration purposes. So here we are in Neo4j browser, where we can run queries and we can explore the graph. So we can see that my graph contains 2 node labels, one called character and the other called house. It's actually a graph representing the Game of Thrones characters. And there are 2 types of relationship. One is the belongs to, so where a character basically belongs to a house. And then we have the interacts relationship, where a character is actually interacting with others. So that's an example of a part of the graph that I'm using. So let's see how we can first get this graph data science library. It's really super easy because in your so in the app called Neo4j Desktop, where you manage all your graph, you just have to go to this plugin tab, check the graph data science library, and click install. It will download the plugin, put it in the right place, and restart your database for you. So it's really super easy. So what we're going to do is to run some centrality and community detection algorithm on this graph. And one of the advantages of the graph data science library is that you can create what is called a projected graph, meaning that you can select the nodes, the relationships, and the properties that are in your graph to be loaded into memory. And only those entities will be used for the algorithm. So that's really useful when you have a big graph with many entities. Most of the time, not all of them are useful for your analysis. So you can really reduce the memory usage to only what is important for you. So the way we
Estelle,
do that.
may I request you to zoom in a little bit?
Sure. Up, here we are.
Yeah, perfect. Thank you.
You're welcome. So here what we're doing, so it's just calling this procedure GDS graph create. We are going to create a graph called graph, and we include into that graph all the nodes with the labeled characters and all the relationships of type interacts. And we're just specifying that this relationship must be understood as undirected. So we can run this query, which run without any error. So it means that our graph is now loaded into our memory, and now we can run an algorithm on this graph. So here is the PageRank algorithm that runs on our graph, and that returns for each node in the graph a score corresponding to the importance of that node. What we're doing is we're just selecting the 10 top 10 most important nodes in the graph. So the algorithm runs very fast, as you can see. The results are not cached. It's really the real-time demonstration. And here you can see that our most important nodes in terms of interaction in the Game of Thrones graph, we have as most important node Jon Snow, and then we have some other characters, Lannister, and so on. So characters that appear a lot in the books and in the series. I've not watched the series and I know those names, so there might be important. So here we have used a stream, a way to get the results. So the results are just displayed in my browser. There is another way to actually run the algorithm, which is to use a write procedure. In that case, the algorithm will be run, and instead of displaying the result, the score, the PageRank score, will be stored as a property attached to each node. So we can do it. And here, if I look at some of the nodes, you can see here that we have a new property called PR attached to each node. If we want to run community detection algorithm, for instance, one algorithm is called Louvain, which is just the name of the university where this algorithm was invented. We can do the same, and here we have attached to each node a property called Louvain with the result of the community detection. So if we check again here, now you see that we have a new property called Louvain with the name of the ID of the community it was attached to. So that's how you run algorithm in Neo4j very easily. Next, I want to show you how you can extract this information and basically fill a data frame to then run any algorithm. So first, we have to install one package, which is simply called Neo4j. So I've already done it, so I won't run it again. And then we just have to create a driver with the connection string like we would do for any database. So for instance, if I want to retrieve all the characters, their name, the Louvain community they were classified into, and the page rank, their page rank score, I would write this is Cypher query. And then I can simply run the query and get the records by using the data method here. So here I have a list of dictionaries, and thanks to the pandas from record method, I can import this data into a data frame. So here I have a data frame where each row corresponds to a node. And I have some what I call graph-based features because they were computed with graph algorithm thanks to the fact that I have identified the interactions between the different characters. I could not have this Louvain and PageRank feature only by reading the books and extracting, I don't know, the age or the house of each character. So that's the next step when you're trying to do some graph analytics. You start by traversing your graph by doing some Cypher queries, and then you can use graph algorithm to understand your graph, understand the communities in your graph, understand which are the most important nodes in your graph, and then you can use the results of this algorithm to create new features to build node classification models, for instance. Last thing I want to talk about, so very quickly, is some words about graph deep learning. So basically, now we are still in the phase where we are manually building features. And we know that deep learning, especially thanks to embedding, allow us to learn the features from our data. So embedding, I guess you might have heard about it, but if we take the example of a word embedding, which is maybe the easier to understand, the goal is to find a vector representation of a word, so transform a word to a vector that is understandable by a machine learning algorithm in a way that the dimension of this vector is quite small. So it's not a one hot encoded word from a huge dictionary where you will have millions of elements in a matrix. So we try to reduce the size of this matrix, but we want to keep some meaning about the word. So I really like this picture that shows that when you go from a man to a king, the distance between the man and the king is the same as the distance between a woman and a queen. So by that I mean that the kingness is kind of conserved. One way to compute word embedding is to use the word context. So you start from a word and you look at the words next to it, and then you kind of count how many times those words appear together. And you have like this a kind of context-based embedding. And by that, you know that cute and cat might appear together very frequently. When we talk about the graph, we do not have this one hot encoded dictionary, but we have the adjacency matrix. So the adjacency matrix has a size also n by n, where n is the number of nodes in your graph. And the elements of the matrix represent the fact that there is a relationship between the nodes or not. So on this graph, for instance, you see that there is a relationship between node A and B, and it's represented by the 1 in the first row and second column of the matrix. So this is also a very big matrix when you have a very big graph. So it's not usable. One way actually to generate embedding for a graph, or more precisely for nodes of your graph, is to use a random walk. So with the same ID as the word embedding, we are actually creating sentences by traversing our graph. So for instance, here I have the sentence BAD because the path BAD is a feasible path in my graph. I couldn't have CDA, for instance, because I could not go from C to G with this graph. There is no relationship between C and D. So this is actually the deep walk algorithm, how the deep walk algorithm is working. And you see that it takes a graph as input, and the output is a vector representation of your node, where the nodes that are close to each other in the graph are also close to each other in the vector representation. So you see in the top figure here that the red nodes close to each other in the graph representation are also close to each other in the vectorial representation. The problem of this algorithm is that it's called transductive. That means that if you add a new node to your graph, you cannot infer the embedding from the already computed embedding. You will have to rerun the algorithm again, and the embedding might change a lot. So another algorithm that is used for node embedding and that actually solve this problem of transductivity is called graph sage, where basically instead of learning the embedding, the algorithm learns the function to compute the embedding, which is one step further, and that allows to compute the embedding of an unknown node that has just been added to the graph. So I will just skip the details here. They're maybe a bit tough. And I will just show you how you can compute the node embedding with the graph data science library. So we are going to use a similar query compared to the one we have used before. So for now, graph sage algorithm is still in the beta version, but it's already available and you can try it. We are going to train that model on the projected graph we have created before, containing the characters and the interactions relationship. And we are going to store the trained model into the embedding graph sage 1 model. And we are also specifying here the size of the embedding we want at the end. So I've just run the algorithm for an embedding size of 2. So the each node will have at the end 2 features. So here we have our trained model, and now we can use this, run this model to extract the embedding for each node in our graph by using, for instance, the stream procedure we have seen earlier, and here repeating the name of the model we have just trained. So if we run this procedure, we see that for each node, we have a list here of 2 elements corresponding to their vectorial representation in the graph. And with a bit of pandas magic, you can just transform this into separate columns. And here we have features that were automatically learned from the graph and the graph structure. So these numbers takes into account the fact that two nodes are close to each other or not. And graph stage has the also the really interesting feature of being able to take into account node characteristics. So if we already have some ideas, some features about our node, we can also include them into the model. So let me just summarize quickly. So you see that if you are willing to use a graph database for your analysis, you first have to think about building a knowledge graph, meaning importing your data into a graph. So thinking about your data model, what are your nodes, what are your relationships. Then you can use Cypher and build some queries to understand your graph, to do some aggregates and characterize your graph. Once you have a better idea about your graph, you can use a graph algorithm to get even more information about your graph. And finally, you can also go one step further and learn the features from the graph itself. So that's all I wanted to show you today. If you're interested into this topic, you have a lot of information out there. Especially Neo4j guys have released two free books that you can download to learn more about graph algorithm and graph data science. And you have also graph-powered machine learning, which is really useful if you are interested in recommendation or fraud detection. Alessandro, who is the author of this book, has done a really great job in showing you different techniques to build that kind of application from graph databases. And hands-on graph analytics with Neo4j is the book I have authored, and it's more focused on the algorithm, so how the algorithm are working and in which case you might use which algorithm and how to connect that to a graph data science pipeline. So thank you very much for listening.